Hello, welcome everybody. We start Verônica's Master's Qualify now. I'm glad to present this qualification for a team, international team with the Professor Kazuo Okanoya from Japan and Renata Sousa-Lima from Brazil and University of Rio Grande do Norte. And Verônica has 50 minutes to present her work. And after we can continue and go with the considerations of the members. Welcome and thank you for accept our invitation.
Hi, I am Kazuo Okanoya from Japan, and I study bird song, especially Bengali finches, and also a lot of the sound communications. So I enjoyed Veronica's thesis, and I have several comments on that.
And I'm Renata Sousa-Lima. I thank you, Malu and Verônica, for the invitation. I work with bio and ecoacoustics here in Brazil, focusing on signal evolution also. So I did enjoy your work because one of my main interests is also the disturbance and influence of noise on bio and ecoacoustic patterns.
Thank you. And Verônica, you can already start your presentation. Thank you, Verônica.
Okay, so welcome everybody. As Malu said, I'm going to present my master's degree qualification exam. My research is about the influences of urban noise in the songs of Zonotrichia capensis and Turdus rufiventris. It was guided by the Professor Luisa da Silva at the University of São Paulo. And that will be my sequence presentation. First, I will give some context in the introduction and my project planning, then the results, discussion, and conclusion. So let's start talking about bird songs and urban noise. And first of all, I'd like to define what is sound. So every time we play an instrument or talk, we are creating vibrations, as in the harp string. And now around the harp string, there are air molecules, and when the string vibrates, it will push the molecules away, and then they will push another molecules until we have a wave of molecules being pushed in some direction. And that is what we call the sound wave. So as in the video, if we follow a single molecule, we can see the sound wave being formed. And the sound can be analyzed by 3 parameters. First, there are frequency, and is measured in hertz, and it represents how fast it will be. So fast, we have a high-frequency sound that has shorter waves and high-pitched sound. And if it moves slow, we have a low-frequency sound that has longer waves and low-pitched sound. So now I will show a low-pitched and a high-pitched sound, and I will ask everybody to turn down your volume. The second parameter is the amplitude, and as in the video, it represents how far the molecule is going from its original point, and is also called the intensity. It's measured in decibels. And the last one is time, is measured in seconds, and represents for how long the molecule is vibrating. Using these 3 parameters, we can represent the sound as an image, and it's called sonogram. In the y-axis, we have the frequency, and in the x-line, we have the time. and the opacity of the image represents the birdsong intensity. So here you have a birdsong being represented. And for birds, acoustic signals related to specific individual recognition are called song, and the song is related with mating, territory defense, and can show physical and ontogenetical conditions from the individual through communication. So what is communication? It happens when you have an individual sending a signal, and that signal will pass through environmental restrictions as noise. And that modified signal will be received by another individual and will result in an answer. In my project, we are focusing on noise. So while the bird is receiving the signal, it's also receiving another set of sounds that is not a signal. And that's noise. Any sound that isn't a part of the signal sent and decreases the detection of the acoustic signals. Between all kinds of noise we can hear, we have the anthropogenic noises, those formed by human activities. And they are important to study because until 2050, it's expected that 68% of the human population will be living in cities. And among all common sources of noise, we have transportation. So here we have airplanes, motorcycles, subways, cars, and buses. And that is their relative intensity noise. Also, urban sounds generally have frequencies up to 2000 Hz. So here in the sonogram, we can see that the anthropogenic noises form a really dark line, and that means that they have a high intensity. And also we can see that the traffic jam is overlapping the birdsong frequency. So how anthropogenic noises affect birds? There are evidence that noise at 76 to 106 decibels can cause temporary hearing loss, and a high-intensity noise for long periods can cause a permanent increase in the hearing threshold. The hearing threshold is the minimum intensity necessary for the bird to listen. Along with that, we have the effect of masking, that is the increase in the perception threshold due to the presence of another sound. So the song's variations due to masking can occur in all axes of the acoustic space. So now I will show which modifications we can observe in the bird song. Starting with amplitude, we have the Lombard effect, that is increasing the birdsong intensity because the presence of noise, and it's related with noise levels and communication difficulty. Related to frequency, we can observe an increase in the minimum frequency, and it will be stronger as the noise has the same frequency as the bird song. And related with time, we have shorter songs and shorter intervals, as well as longer songs, and the song intercalated with noise, trying to avoid overlapping. Besides these changes in the physical parameters, we also have changes in the birdsong complexity. So it will be more redundant and have introductory notes with low information. But how one can define and measure complexity? That question leads us to the next part, that is entropy and Markov chain. As we saw, the birdsong has information, and information can be analyzed by the information theory. The information theory analyzes the message by the amount of information, and information is described by the authors as freedom in selecting a message. And they measured it by entropy, that is the predictability of the message. So to understand better, it's like when we are sending a text to someone, we can say the same thing in many different ways. And a similar thing can occur to animals. When they are sending the signal, they can choose the best way to send this signal. And every part of the signal will have an amount of information. That means that every part will be less or more predictable. And all these probabilities comes Markov chain. Markov chain illustrates the transition between each state within the phrase. And Markov chain has to follow some properties. The first one is that the probability of each new state doesn't depend of any previous events. So when you are passing from the green one to the pink one, doesn't matter if before was the brown one or the blue one, because the probability will be the same in both cases. Another property is that when the current state changes, there's a probability for each new possible state to occur. So every time you have a transition, we have a chance for something to occur. So using this, we can analyze the information within the signal, and so we can analyze the complexity in the bird song. And the stereotype will be greater as much as the elements are predictable. Also, using these tools, we can analyze the effect of urban noise in the bird sound complexity. However, when we search for papers, we only see papers analyze the diversity of the elements in the bird song, and usually they use European and North American species. So we decided to study how urban noise can affect bird song using 2 Brazilian bird species. They are the Zonotrichia capensis, the rufous-colored sparrow, and Turdus rufiventris, the rufous-bellied thrush. Both species are very common and have a wide distribution, but Zonotrichia capensis has a song without variation, while Turdus rufiventris has a song with many variations. And now I show our goals and our hypotheses. So we want to evaluate urban noise influences on these 2 Brazilian bird species by measuring the physical parameters, and then we expect a higher minimum frequency and higher phrase interval in the urban environment. By measuring song complexity, we expect a more stereotyped songs in the urban environment with less sequence variations. And by analyzing the entropy, we expect a more stereotyped songs in urban environment by repeating the same notes. So now I'll show our project planning. First, the places we recorded the species. They were separated into 2 groups. The first one was called the conserved environment, and it has lower noise levels and was composed by conservation units and rural places. The other one was called the urban environment, and it has higher noise levels and was composed by municipal parks and streets where the species could be found. For the field sampling, we identified the species by seeing and making playback, and we recorded the species between August to January because that was the reproduction period of the species. Remember that birdsong is related with mating. And after filtering the songs that could be analyzed, we had for Zonotrichia capensis 30 songs in conserved places and 7 in urban places. And for Turdus rufiventris, we had 21 in conserved and 11 in urban places. To measure the physical parameters, you used the Haven Pro software, and first we assigned the unit song as note and a sequence of notes as phrase. Then measure the note and phrase interval, duration, minimum frequency, and maximum frequency. To organize the data collected, we made a table for each species, and here's an example for Turdus rufiventris. The first table had the physical parameters in the columns and each note in the rows, and the second table had the average of the physical parameters in the columns and each recording in the rows. Then, using the RStudio software, we created 2 new tables from the first one with just recording from conserved places and another with just recording from urban places. And from the second table, we created 2 new ones, one with just temporal measurements and another with just frequency measurements. Then we did the statistical analysis. Again, using the RStudio software, we did Shapiro's test to see if the data has normal distribution, and as it didn't have, we chose to make the Mann-Whitney test to compare the 2 environments. Using the other tables, we did the coming clustering analysis, and that analysis separated each recording in a different group based on their similarity. And finally, for Markov chain, we assigned a letter for each unit song, and the first note in the first phrase was the letter A, the second note in the first phrase was the letter B, and so on, and the same unit song received the same letter. Then we wrote the note sequences and calculated the probability for each transition. After that, we created a list with every transition, their probability, and the number of occurrences. And using the GIF software, we created a directed graph that represents all the node sequences possible. So now I'll show our results with this analysis. As the data didn't have a normal distribution, we decided to make histograms to see how the data was dispersed. And we already could see that the urban environment was clearly separated from the conserved environment. So the urban is the gray one, and the conserved is the green one. And they are separated except for the minimum frequency. And when we did the test, the frequency range and the maximum frequency had the higher measurement from the urban environment. And when we did the test, we could see that all parameters were different between the environments except for the minimum frequency. So if we see the box plot, we can see that they are clearly different except for the minimum frequency. And we also found that by the coming clustering analysis. So here are the clusters made from temporal measurements. This purple one was just made from recordings from the urban place, except for the one circled. And the brown one had just recording from the conserved places, except for the one circled. Also, if we look for the y-axis, the phrase interval, we can see that the urban environment has higher values than a conserved environment. For the clusters made with temporal measurements, we also found that both environments were different with the frequency measurements. So here you have a cluster made with just conserved places and another with just urban places. And this clustering has a 93% of being representative. Then we decide to compare results with other studies. The pink lines mark the results that were different from our results, the studies that were different from our results. And the green lines, the results that were similar from other studies. So we also found the same results for the maximum frequency, but the different results from minimum frequency and delta frequency. And it's interesting to note the minimum frequency was different because there are many studies that show it a higher minimum frequency in the urban environment. For the temporal measurements, we also found a phrase duration that is higher in the urban environment, but we found a different result for phrase interval. And here's the summary of the comparison. And for Turdus rufiventris, again, we did the histograms, but we couldn't see a clear division between the environments. But making the test, we found that all parameters were different between the environments except for delta frequency. So again, we can see that they are different. The median is different for delta frequency. That is the difference between the minimum and maximum frequency. But for the coming clustering analysis, we didn't find the difference between the environments. So here is the cluster made with temporal measurements. Basically, all the recordings were put in the same group. And for frequency measurements, we have both clusters with recordings from both environments. And for some complexity, we found that songs from urban environment are more stereotyped than those for conserved environment. And we can see that by analyzing the directed graph. So here's the graph, and every gray circle represents a note. The beginning circle represents the beginning of the phrase, and then circle the ending of the phrase. Every arrow represents the sequence, and the thickness of the arrow represents the number of occurrences. So the more it is sticky and red, it represents that it occurred more times. And when we compare the environments, here each image is from one environment. We can see that the urban environment repeated fewer notes and had less possible sequences. We can see that better if we take each recording from one environment and detail it. So here we have this board is every phrase from this recording, and is the same recording represented in the graph. And the painted square represented the 9 note sequences repeated in the graph. The same is for the gray board. Here's the 2 note sequences that is repeated in the graph. So when you compare the two boards, we can see that the urban environment is repeating fewer notes than the conserved environment. Here's a summary of all the results. For the physical parameters, we found a significant p-value for all the physical parameters, except for the minimum frequency. And usually the values were higher in the urban environment. For the coming clustering analysis, we found that the phrase interval is higher in the urban environment, and that the frequency measurements can separate the environments. For Turdus rufiventris, we also found a significant p-value for all the physical parameters, except for the delta frequency, and they usually were higher in the urban environment. For the coming clustering analysis, we couldn't find the difference between the environments, neither using temporal measurements or frequency measurements. And for some complexity, we could see that the urban environment has less note sequences and repeated fewer notes. So now I show our conclusions. For Zonotrichia capensis, we found that the physical parameters differ between conserved and urban environments, except for the minimum frequency. And for Turdus rufiventris, we found that the sum complexity differs between conserved and urban environments. Here's my schedule for my next year. We want to analyze more recordings, and by August, I would like to make my thesis defense. And that's it. I would like to thank you, my colleagues from my lab, my institute, and my financial program, and especially for everyone that helped me all this time. And everybody here, thank you.
Good. Very good. So, I think I can continue with these advisors' considerations, and I will pass the I think Kazuo, Professor Kazuo Okanoya can speak now.
Yes.
Your considerations. Thank you.
Yeah. It was very well organized, very professional, and also very kind to listeners with many diagrams and figures. So the presentation was very nice. And I have several comments that can be divided into the information we need more. And well, okay, I have comments about information and about species selection and about hypotheses and about analysis. Okay, and about information, I thought it will be much nicer if you can provide long-term average spectrum and of each environment. You see, the spectrum, I mean that the horizontal axis is frequency, the vertical axis is intensity, and if you have the distribution of noise, environmental noise for urban environment and what is it, protected, conserved environment, then we know the nature of their habitat, and we can correlate that data with your finding. That's one data, one information I would really like to have. And in your final master's thesis, I recommend you to have that. Okay. Okay. Next, about species selection. I I would like to know more about why you selected these two species. I understand that Zonotrichia species is more, they sing simpler song, and what are the other one? Turdus.
Turdus.
Turdus species sings more complex one. That's one thing. I would like to know why you selected these two species. I understand songs are different. However, there should be some other differences like learnability, how much innate constraints are there in each species. And I understand you analyzed sequential Markovian analysis only on the Turdus species, not on Zonotrichia species. I guess this is because Zonotrichia species sequence is so fixed. Is it true? Is it true? Okay.
Can I speak a little bit? What do you think? We should keep just Turdus? Because I'm thinking about that because it's the more complex. It makes sense, more sense to analyze Turdus.
Well,
What do you think?
I mean, rather than comparing two species, you mean?
Yeah. I think
Well,
I was thinking about that yesterday. I think it's too much to keep two species. Maybe
well,
Turdus is a better model.
no, I actually think comparing these species is very interesting, and the result is so different. And I think it's very important to show two species. And if you are doing that, I would rather recommend you to do the same Markovian analysis, although Zonotrichia song is much simpler.
Could I make a question about it?
Yeah.
Because I couldn't find the dialect of the Zonotrichia capensis because I only found few individuals from each place, so I couldn't do the dialect of the population. So I don't think I can compare without the dialect.
Okay. Okay. Yeah. Okay. Okay. So, the other than the Markovian analysis, you are basically doing the same analysis for two species. Is it right? Right? Yeah.
Yeah.
Yeah. Okay. Then, okay, I understand that it's difficult to do the Markovian sequential analysis in Zonotrichia species, so it's okay. And I repeat that I need to know why you selected these species, and it should have some rationale. Why this species I can see this, and with this species I can see this, right? And in your thesis, I think you are hypothesizing that Zonotrichia species is more, song should change more in Zonotrichia than Turdus. Is it right, or am I making mistake?
Zonotrichia is more. It has dialects.
Let Veronica answer.
Yeah. Let's go on.
It is because
Okay.
Zonotrichia capensis has dialects, so the same individual, the same population will sing the same song, and they won't vary. This has some variations between the populations. So, is that what I wanted to say? The Turdus has variations within the song from the same individual and between individuals and between populations, but Zonotrichia only has variations between populations. And as I just found few individuals per populations, I couldn't see which one was the dialect from that population.
Oh, okay. Please explain that about species selection more, and about analysis. Okay, why you use k-means rather than just a dendritic clustering method? That's one thing I wondered.
The coming clustering analysis was a way of seeing if the data has some differences we could delineate by just making the box plot. And so the coming clustering is a way of asking for the computer to find the difference for us. And as it really found differences between the two environments for Zonotrichia, and we could see that the phrase interval was higher. So it was two analyses that confirmed the same result.
Okay, well, if I were you, I would not use k-means. I will use multi-dimensional scaling. Yeah, because k-means have a stronger assumption in doing analysis. So it's okay, but please state clearly why you selected to use k-means. And if you have some time to try out multi-dimensional scaling, it should also work. Okay, and also about Markovian analysis. You show the transition diagram. It's okay. However, if you can draw some number, one number that states how complex it is and how simple it is, will be nicer.
Just to be sure, you'd like that I put the probabilities in the graph?
Yeah.
Okay. Yeah, that was a problem because when I did in the RStudio software, I could put the probabilities, but the graph was a mess. And so I decided to use the Gephi, but Gephi didn't put numbers in the graph. So, or I did it by
Well, that's the graph is okay, but for each graph, if you can make one number that simply stating the complexity of a graph, it will be nice. And in the very classical study by Constance Scherf and Fernando Nottebohm, they are using index, so-called linearity index. You know that? Okay, it's one way to express in a simple term. Linearity index is a possible transition. No, I forgot. Linearity index, you can very easily calculate a linearity index. If you have the matrix of transition, then you can do that. So please try to think about that.
I think Gephi calculated that automatically. I just didn't put in a number. Yes, that was a problem.
Well, you have to do by your
Renata, you'd like to talk?
If Dr. Okanoya will excuse me just to give another suggestion. There's also Levenstein distances that will also give the sort of index. Yeah. So it might be a little like a steep learning curve, but it also shows complexity in comparing strings. And you can do that for birds as well.
Okay, so my comment is that's all. I think this is what I thought. These comments. I have a note, so if you like to have a note, I will send you a note. Okay. Oh, and one more thing actually. We actually have done Lambert effect experiment in Bengalese finches. And we compared undirected singing, which is complex, and the direct singing, which is simple. And we found that complex undirected singing has stronger effect of background noise. Okay, so, and we also have a paper comparing that syllable type and effect of background noise. If you try to find by my name, or I can send you reference actually, I already wrote all these comments on your paper, including the reference. So I'll send you the paper. Okay. So okay. So I'm done. Thank you very much, and it was very fun. I mean, interesting to study your thesis. Thank you very much.
Thank you for your contributions, precious contributions. Thank you very much. And now I think Renata can present her contributions. Thank you, Renata.
You're welcome. Thank you. Verônica, congratulations. I also enjoyed very much listening to your presentation and watching you present. You're a very good presenter. You presented very clearly. I love the slides, the animations, very didactic. So it's very easy to understand your points. I have a few suggestions to improve even further your next presentation for your defense, and a few points that I'd like to discuss with you that are more theoretical and your understanding of the theory behind animal communication, and to sort of tease you to look into that a little more. So I'll start commenting on the text of your document. So I think you can still check the grammar and the spelling in English. There are some prepositions that are missing. Some phrases are not very clear. And as I tell my students, when you're going to submit, the quality of your paper, it's the result of the clarity of the ideas that you put on your paper. If you have a very good idea, but it's not well explained or broken down in logical steps, the great idea is going to result in a bad paper. So if you have a very simple idea and you have a very good objective way to write that idea on paper, you have a very good paper. So clarity is quality. That's what I keep saying to my students. So I also thought that a few references were missing, and that you should substitute some references with more original work, and not work that cited the idea that you were mentioning. So sometimes you cite a paper, but somebody else way before said that. So you should cite the original paper. So I can, make a note on the document for you, and I can, send it to you. There is a very good meta-analysis by one of my students, Lidiana Gomes et al., about this, how the animals and how different taxa compensate on vocal parameters when they're exposed to noise. So you should look into that, and it will give you a very good idea of, she did a very good job on revising the literature, so that will help you in doing and revising your references. I was curious I'm going to comment in a few points, and a little less objective than Dr. Okanoya, which was great and objective. I'm going to be more Brazilian and less objective, I guess. But I think it's important for you to think about those things. You write in the beginning of your text that song is important for survival and reproduction. So I was curious.
Are you
Yeah.
looking in the text? Could you say the
No,
page
I'm
for me?
not. I'm
No,
not looking
okay.
at the text.
Okay.
I took notes. It's just a conversation about theory. So I was curious to understand, for you to explain in more detail for me how song influenced survival.
Okay. Okay, maybe I wasn't so clear. I put some examples like it's related with reproduction and territorial defense. So for me, that is already answering that. No, that's already proving that it's important to survivor because it needs the territory to eat and it needs to reproduce to pass their DNA. So for me, my idea, I thought that was enough. I don't know what would you think that would be great to put together.
No, I think it's great that you answered like you did, but see that you started your justification about survival with the reproduction, right? So song mediates intra and intersexual reproduction, selection. So it's a means to get to the end, which is copulate. So if you defend a territory, you defend it probably to attract a partner or to fend off, opposition, a competitor for your partner. But what I think it's interesting is that you later said that you need the resources on your territory. So that's the justification. But I think in the text, it wasn't very clear for me that it was clear for you. Okay, so try to make it a little more clear with, talking about, resource holding potential for the individual and for their partner. So it plays both roles in survival and reproduction. Something else that caught my attention is, I teach animal communication, so I discuss this a lot with my students. And it's the concept or the definition of what it is, animal communication, what's a signal. And you did a very good job at defining it right off the bat, because there's so many definitions that we need to know what the writer is working with, what's his working definition of animal communication. And you said that it needs to be intentional and it requires a response. I personally don't like that definition. I think it's too limiting, because sometimes you do have a signal that evolved, but you have no response, because the response is a privilege of the receiver. And the receiver might choose to ignore it, even though he received the signal, interpreted the signal, and made a decision to ignore it. So what do you think about these things? Yes, Malu?
The response can be silence.
Yeah, I would
Silence
say
is
that.
a response.
I think it is still a response, even if the other individual didn't receive it clearly. But the individual is having a response. So it's having a response. The response exists.
Okay,
but
so let me give you another. It's a provocation, okay? It's just to get you thinking.
Okay.
If a bird is alone in a territory, there's nobody listening, and it goes to the tip of the branch and starts singing, is it a signal? There's no receiver. So if there's no receiver, there will be no response, even if it's to ignore it. I don't need an answer right now.
Okay.
Okay, I just need you to make sure that you want to work with that definition for for the work that
In
you're
the
going to be doing.
definition, it's not a communication. The majority of the authors, if no one is, there is no one, there is no communication. Alarm call, sometimes some definitions say that is not communication because it's not directed to a receiver. but it's in theory. And we're talking about the gregarious species, so this situation, I think it's too almost impossible.
Yeah, Veronica, but you should make sure that you're getting a PhD in animal communication. So you need to think
No, it's
about those
masters.
things.
That's master.
Oh, it's a master's. I'm sorry, a master's. Even though it's a master's, you're going to be a researcher working with that. So I like to provoke people to think and to make sure that they know what they put in the paper is actually what they think theoretically in the back of their heads. So I have a very important point to make, which is a point that always shows up in reviewers and in most of my editing jobs. I see that when people are analyzing different populations with different noise levels in their habitats. So you yourself said that, let me see if I can find it in my, you said that there is variation in the Turdus, that there's individual variation, there is group variation, there is population variation, right? So my question to you is, how did you control that? So do you think it's possible that the variation that you found between the two different noise level habitats could actually be a variation that is inherited or that is intrinsic to the levels of variation of that population, like geographical variation, dialects, different individuals that might have different voices? Do you think that's possible, and how did you control it?
I think that it's an interesting note to put in the results too, because as I said, there are many variables. If there is a big population, it will vary the song. If it's the vegetation will vary the song, many things can vary. So my intention was to try to take many different habitats conditions, so populations that are big, populations that are fewer, and then compare them, because that will be some kind of differences. Also, I recorded in streets and parks that could be a variation because of the vegetation, and that also could be included in some form in my study. So I tried to control with these things.
So you tried to control with replicates, which is great.
Yeah.
You know, so thank you very much for your response, because that's when we cannot control something, like you can't control that, right? It was a trick question. You can't control it unless you take the same individual and expose that individual to two different conditions for noise exposure, like what Dr. Okanoya did with his finches, right? And or Zollinger did that. A bunch of people did that, and they found different things. And or you actually have lots and lots and lots of replicates of samples. So that's my next question. How big was your sample? I haven't seen a sample size number in your presentation.
Okay.
So my question is, how big is your pretend, the sample that you want to collect? How much have you processed, and how much are you still going to collect?
Okay. I tried to list Malu, if you want to. I don't know
she's frozen, or maybe
yeah. I will
her?
answer until she returns.
Okay.
I tried to record at least 10 individuals per species per location. So every conservation unit has a nucleus, and I recorded in every nucleus. And every nucleus, I tried to record at least 10 individuals from there. So in the conservation units, I had in both 20 or 30 individuals. I don't know by mind now. And in the streets, I had also 10 in streets and another 5 in each municipal parks.
So you're considering the individual, and then if you get like 100 songs from one individual, you use those 100 songs, or do you use like a mean of that individual?
I used the mean, and I used it like I had like the mean per individual, the mean per location, and then the mean per environment.
Great.
I think I have these 3 parameters.
Good. Because, I mean, I know you are aware of that because you have a very good supervisor, but some people use all the songs and then it becomes pseudo replication. So it's not really replication. And so talking about yes,
there is no dialects in Turdus, no populational difference, just individual difference. And we have found, I published some articles about the code, the specific code that encoded in the rhythm of the song. But the sequence, for example, it's always variated within individuals. So it's a special case, the thrushes.
Important then to tease out the parameters that vary geographically, like what you know, to avoid that, or to control a little bit of what could be a problem when you submit your paper. So the sample size, apparently it's good. So thank you. And let me continue my notes here. The way you wrote your specific goals in your document, it takes us to a causation relationship. And I don't think you can say that. So I would rewrite it to be, influence or explain, or there's an effect, just to make sure, because you're not looking for causation. You're looking for an effect of noise on vocal parameters. I was also curious when I wrote that you put public transportation is the major contribution to noise in terrestrial habitats. Why only public?
Because there were some places, like in the conservation units or around the municipal parks, that the majority of the sounds were public transportation. Traffic jam was higher, and airplane, we could listen all the time. So I thought that was the main sound I was listening, so that would be an important sound to take, to analyze.
But you need to show us that, with numbers, with data. You can't just say, oh, I think I heard more of that than this. So I love the idea of Dr. Okanoya to have long-term spectrograms. And I will add to his suggestion that there is a very good way to visually understand the energy budget and the noise budget in an environment. And it's a ribbon plot. You can look into Townsend's work with Paul Rowe, the Australian people that work with soundscapes. And it's like you can calculate three indices for your soundscape and plot them in different colors. And the colors will combine to make a different color. So you're going to start seeing patterns of things, and you can see patterns of trucks and cars and noise, and you can see patterns of your birds also probably. And using ribbon plots, you can see that through time. So you can see if you use what a long-term spectrogram, you're getting the mean for their environment, which is very good because you have an overall sense of how noisy or not the environment is, but you don't have any measure of how variable or how noise fluctuates in that environment. And that might be very interesting for you and for readers to see, especially because you have different sites within the urban
Environment.
Habitat and within like the more pristine conserved habitat.
Could I ask you to put the paper title when you send your notes?
Yes. Okay.
Thank you.
I will. I'll send the ribbon plot references for you. You also said that masking. You talked a lot about masking, right, on your rationale, and it's linked to frequency overlap. And that's one of my most important questions for you here. Do you think if two sounds are in the same frequency, like the signal and some noise are in the same frequency, that there's always masking?
I'm not sure. I think it depends on the species, because there was a reference I put that the bird tried to intercalate the song with the noise, so it wouldn't overlap because it was intercalating. But I think for Turdus and for Zonotrichia it is true, because in many sonograms I saw they singing in the same time that was the noise. So there was overlapping.
And it was always masked for you? You said that masking is when all of a sudden the sound is less detectable, right? Because it's embedded in noise, right? But for that to be true, and that's why I wanted to get to, the noise level needs to be high enough that will drown the signal into it, so it becomes less detectable. So it's not only linked to frequency overlap, it's linked to the sound pressure level, the sound level of the noise, right? And there you have all the Lombard effect that you see clearly when the noise level rises as well as the signal. So you see a clear correlation of noise and signal output. So the animal is actually
singing louder.
Yes, and into that, I wanted to link that to the model selection issue that Dr. Okanoya raised, which I thought was brilliant. And you didn't discuss it at all. I mean, I thought it was really interesting that you have, two birds, one that varies a lot, one that varies very little, and you didn't discuss that, or you didn't make up any predictions about that. So, and in your presentation, when you present your results, try to put the prediction at the same time at the result, so we remember what you predicted and if your prediction received any support or not, because that's kind of nice when you see predictions and results together. So effective communication can be maintained without changing any parameter of the signal in noise, because obviously there's displacement, there's spectral displacement, right? What you're talking about when you're masked, but you can displace yourself spatially or temporally. Like you just said, your birds were singing where it was a little bit quieter. So you can displace yourself to a quieter place. You can displace yourself to a quieter time, or if you can't do that, if you need to to be vocal at that time in noise, then you're going to spend energy displacing in the spectrum, right? So try to remember those two things too, because you didn't mention it at all, that animals can actually leave that noisy place. And Marina Duarte has a really good paper on, I think it's Current Biology or something like that. I think it's a 2011 paper that she showed that marmosets in an urban park, they were fleeing from the parts of the park that were more noisy, even though there was more resources, more food there. And during quiet times, they were actually going to this other place that had more resources. So they're actually displacing themselves in space to escape noise. So they have several types of strategies to deal with noise, not only vocal, not only that. So you have to remember that, because you need to be the bird and know, that decision that it makes at that place. And discuss that within an urban environment. Where can you go, right? So that's an important thing to discuss in your thesis. Let's see. You talked about the introductory notes in noise, right? But you didn't tell us, how does that help?
It's funny because some of my lab mates asked the same question for me.
I know. I just want to know if you know.
It's because it's like trying to ask for attention before the song with the information starts. Yeah. I didn't mention.
Yes, very, very good. Yes. So let me see if there's anything more. One thing that I work with whales, which are completely different from birds, but not. They actually are very similar to birds. So humpback whales have also this complex song, right? And I had a student measuring complexity and comparing complexity, just counting notes, note types. So a very easy measure of complexity is the size of the repertoire, because with a bigger repertoire, the possible combinations scale up, and they can scale up exponentially. And you did say that there are more notes and less notes, right? So maybe it's something that you can easily count and add to your analyses.
In fact, I think I already counted. I just didn't compare, because in the text, in one of the appendix, is the table with all the notes and their number of occurrences. So I already have this.
Oh, good.
I just
good.
did compare.
Excellent.
The entropy incorporates this information because has the repertoire in the distribution.
Oh, okay. Okay. But it's an easy way to talk about complexity, and it holds off even for humpback whales.
You need this information to calculate entropy.
Great. So thank you very much. I think it's a very interesting, an excellent work, and I think there's still room for improvement, but you're in the right course. Thank you very much.
Thank you.
Thank you. You both did very good homework and very precious contribution. And now I think we have to see the note, the concept of this presentation. I think we have to end the transmission for the public, and we keep our transmission here, and after we come back. Thank you very much.
Thank you.
Thank you.
Thank you.
I need your help. I need your help,
Thomas, can help
Tomás.
us.
Hello. You want me to end the presentation at all?
You have to end the presentation for the public and keep
Okay.
us together.
All right. Say goodbye.
And have to silent Verônica.